Well, welcome back, everyone, to today's edition of Four Manifolds in Kirby Calculus. I'd like to thank Jonathan and Jaron for organizing this lecture series. I think it's been very, very well done. So today, I'm going to talk about four manifolds with boundary. And yesterday, Jonathan told us about these algebraic objects we can associate to closed four manifolds called intersection forms. And the point of today's lecture is that, well, we can define the same kind of object for four manifolds with boundary. So for M, a compact orientable four manifold with non-empty boundary, we can also define this intersection form from the second homology of the four manifold times itself to the integers. And the way that it's defined here, as in the case with enclosed four manifolds, is if we have two homology classes alpha and beta, we'll find surfaces that represent them. We'll find smooth embedded surfaces that represent them and perturb them so that they are transversely intersecting, and we'll take their algebraic intersection number, and that's how we'll define this form. And this is also, by Poincare duality, equivalent to an intersection form or a symmetric bilinear pairing on cohomology. But since we have boundary, it won't be the second cohomology of M. It'll be the relative second cohomology of M with respect to the boundary. Oops. And so the way we do this is we'll take, if we have two forms, two cocycles, what we'll do is we'll cup them together. And then we'll evaluate this relative four cocycle on the fundamental class of M relative to the boundary of M. So note, there could be some torsion in these groups, but if A or B is torsion, then QM of AB is 0. So this pairing QM descends to a map on H2M mod torsion. Ooh, oh man, okay. And this form is not necessarily unimodular. That is, if we have a matrix representation for this form, it's not necessarily going to have determinant plus or minus 1. For instance, we can look at this four manifold S2 times D2. And the surface S2 times 0 generates second homology. But if we take the oriented intersection number of F with itself, right, we can push this copy of S2 off of itself completely so that it's disjoint from the original. This will have pairing 0, So here we might represent this as a matrix by just the 1-by-1 matrix whose lone entry is 0. So today we'll focus on a particular kind of four-manifold with boundary, something that we call the trace of a surgery on a framed link in S3. So here's how the construction goes. So we're supposing that we have a framed link in S3, call it L. So we'll thicken S3. So we'll take S3 times an interval. And we're going to let this framed link be inside of the S3 times 1. It's going to be inside of the S3 times 1 component of the boundary of M prime. We're going to leave the S3 times 0 component of the boundary alone. And we're going to attach four-dimensional 2 handles to M prime according to L, right, sitting inside of S3 times 1. As follows. Sorry, I don't know why this keeps scrolling away from me. We're going to attach these four-dimensional 2 handles to this framed link inside of S3 times 1 to form M, which is what we will call the trace of surgery. So, so K is a component of our framed link. And here I've drawn K is the component in blue. The framing, which here I've drawn is the 2 framing of the knot, is in red. And I've drawn it on the boundary of the regular neighborhood of K, or on a regular neighborhood of K. And so the way that we're going to attach this four-dimensional 2 handle, remember it's a D times D, it's D2 times D2 that we're gluing along the boundary of the first D2 times the second D2. So that just looks like a solid torus. And here I've drawn in blue this boundary of D2 times 0 in the second disk. And in red, I've drawn the boundary of D2 times point in the second disk. And this point is just somewhere in the boundary. Oops. And so the way we're going to glue this torus in is we're going to send the blue component to the blue component and the red component to the red component. And up to isotopy, there's a unique way to do this. And it's by just, doing Dane twists of the solid torus, or one way to think of it is doing Dane twists of this solid torus to get the correct framing. Excuse me. So theorem 2.4, gosh, I'm really sorry this keeps happening. Theorem 2.4 in Savelyev is that this manifold M that we get as the trace of surgery is a cobordism from S3 to Dane surgery on this framed link L. And so all I mean by cobordism is that the boundary of M is minus S3 union surgery on L. And the way that we can see this, at least when L has only one component, we can see that the boundary of M has two components. There's S3 times 0, which is oriented by the manifold as minus S3, because we're just taking the product orientation, we're crossing it times an interval, so this end of the boundary is oriented negatively. And then there's the modified S3 times 1 component. So to figure out how this component of the boundary changes after we attach this to handle, we realize that this boundary component is S3 so the boundary, right, this boundary component is homeomorphic to S3. The boundary of the to handle is S3, and they're glued together along in S1 times D2. Right, so if I go back to this picture, these solid tori, well, I guess, yeah, these solid tori are no longer part of the boundary after I've glued this to handle. So the way I can understand what happens when I glue this to handle is I need to look at how D2 times the boundary of D2 is glued to, the exterior of the knot. Right, so the boundary of the to handle decomposes nicely as two solid tori. This S3 that we're gluing to decomposes as a solid torus union the exterior of the knot. And to understand what results, I need to understand how this free part of the boundary of the to handle is glued to the exterior of the knot. Sorry. So going back to my picture again, this red curve, while it appears as a longitude, of the boundary of D2 times D2. This is a meridian of D2 times boundary D2, of the second component of the free part of the boundary of this to handle. And the meridian of this solid torus is just getting glued to the framing of K. And there's a unique way to do that. Right, so the meridian of D2 times the boundary of D2 gets glued to the framing. By definition, this is just surgery. This is just Dane surgery on the knot. Any questions or complaints with that? Does that sound good?
Sounds good to me.
Okay. So obviously, if L has more components, you just do the same thing for each. Yeah, you just do the same thing for each two-handle attachment. I'm sorry this keeps happening. I'll figure this out eventually. Okay, so one nice corollary of this theorem that we've just proved is that every three-manifold is cobordant to S3. And that's because of the Licorice Wallace theorem that so Licorice Wallace theorem says that every three-manifold can be obtained by performing integral surgery on a link in S3. So if we cap off the S3 boundary component of this trace of surgery that we get from this integral surgery on a link, we see that every three-manifold also bounds a four-manifold. So the three-dimensional cobordism group is trivial. Okay, and that's all I wanted to say about that. So now we'd like to understand the intersection form of the trace of a surgery. That'll be the subject that we get into now. We'll look very explicitly at the surfaces in the trace of surgery, as we've been doing in some of the problem sections that we've had this week. So we'll let M be a four-manifold with boundary obtained by the trace of surgery on a framed link in S3. Then the intersection form of this trace is isomorphic to the form presented by the linking matrix of L. So remember this linking matrix of L right, this is just equal to the framing just the framing of the component if I is equal to J, and the linking number of the ith component with the jth component if they're not equal. And this is something that's eminently computable from a link, like a framed link. So in order to proving this theorem, we need to understand the preferred basis of the second homology of this four-manifold that'll allow us to see this equivalence with the linking matrix. So we'll let L be this framed link with N components. If we apply Meyer-Vietoris to the trace of surgery, so we'll view this space as S3 times I glued to these N4 handles along N solid tori. We see that the second homology of this trace is identified with the first homology group of the disjoint union of N solid tori, which is the free abelian group of rank N. And we see that it's generated by the homology classes, it's generated by the homology classes of surfaces AI, obtained by gluing surfaces inside of S3 times I to surfaces inside of the corresponding 2 handle, so that both of these 2 surfaces intersect S3 times 1 and our component and our desired component Ki. And this has been alluded to several times over the course of the lecture series. The schematic here is that if I have an S3 times I, and I have my knot K, inside the boundary, I'm gluing a 2 handle framed according to this framing on K, and I need to take a surface inside and cap it off with the surface in the 2 handle. And so typically, for this Fi, this will be a Seifert surface for K, pushed into the interior. And this GI is going to be the core of the 2 handle. So let's take a closer look at how these 2 pushed-in Seifert surfaces for 2 different components of our link intersect in the interior of S3 times I. So just a toy model. We'll have 2 unknotted components linked once. And remember, we can understand these embedded Seifert surfaces as a movie. With the help of some Morse theory that I'm not going to talk about explicitly. But as I'm starting from, I'll coordinatize I'll just give snapshots of what happens at these different level S3s. So at T equals 1/2, I might see the bottoms of these 2 Seifert surfaces start to appear. T equals 3/4. I'll see level sets of these two surfaces starting to come together. At t equals 4/5, maybe I'll finally see this point of intersection. That's not the one I wanted to draw. I'll see this point of intersection between the two surfaces. And then finally at t equals 1, I see the link that I'm doing, or that I'm attaching two handles to. And so what happens when I pass through a point of intersection between these two surfaces, the linking number, the linking number changes by 1. Well, plus or minus 1, depending on how I orient this stuff. So at least mod 2 the algebraic intersection number between these two surfaces is equal to the linking number of these two components. Right, because I start from an empty link, or sorry, I start with these two components completely unlinked, and by the time I pass through all the intersections between the two surfaces, I get my link, I get the actual link that I care about. So the only issue here is that we need to sort out a way to orient these surfaces so that we don't just get this. We'd like to promote this to an actual on-the-nose equality. So that we can just compute this explicitly and be done with it. And the great thing is, there actually are canonical orientations of these two surfaces that give us this desired equality. And so, ooh, shoot. The sketch of the proof is that if I start with an oriented link, well, then each of these, right, each level set in my movie inherits an orientation just from this link. So in order to compute the oriented intersection number, right, for every point in the intersection of these two surfaces, I need to compare the orientation induced by the intersection against the orientation induced by being a point in S3 times I. And then whether or not the orientation agrees or disagrees, I count that point with sign, plus or minus 1. And so we already have, for each of these points of the intersection, for each of these surfaces, we already have 1/2 of the orientation, and it's given by this tangent vector that's inherited by the orientation of the length that we started with. And so to place the other, right, the other vector that determines this orientation, what I'll do, and this doesn't exist in the time slice of S3 where these two intersecting circles live. These are pointing in the T direction. Well, they're tangent to the surface, but pointing, not in the level S3 direction, but positively into the time direction. And so with this orientation, I'm leaving out the details of the proof, but verify this orientation of Fi achieves this equality. Okay, so this is very handy because this now allows us to complete the proof of Theorem 6.2. And let's remember what that says. Right, that says that Q of M is isomorphic. To the form presented by the linking matrix of L. So remember, we have these distinguished surfaces, AI equals Fi union GI, pushed in Seifert surface, core of 2 handle, so for I not equal to J, the algebraic intersection number of AI and AJ is going to be the algebraic intersection number of Fi with Fj plus the algebraic intersection number of Gi with Gj. But this is 0 because the attaching regions for these two handles are disjoint. So just the cores of these two handles don't intersect at all. And we've already shown that the intersection between these two surfaces, the intersection number is just the linking number of these two components. So now we need to understand what happens when we try to find the self-pairing of one of these surfaces with itself. So what we need to do is we need to perturb AI to some isotopic copy AI prime that intersects AI transversely and so we can push GI off of D2 times 0. But when we do this, so this is to get GI prime. But when we do this, the boundary of GI prime is the Ni framing of Ki. Oh, I didn't give myself enough space. I apologize. Can I insert a new page here? Okay. And this, once we push GI prime off of itself, once we push GI off of itself to get GI prime, we get that these two parallel copies of the core of the two handle are going to be disjoint. So now what we have inside of S3 right? So if the black is the boundary of GI, we now get that the red is just going to be this framing of Ki, right? The boundary of this parallel push-off. But both of these knots bound Seifert surfaces Fi prime. And as we already computed, Fi dot Fi prime is just the linking number between Ki and Ki prime. So this is, I'm abusing notation here. But this, we know, is just given by the framing of Ki. And so the proof is complete. Right, in summary, that's what we have. Oops. Okay. So I wanted to end the lecture by talking about some recent applications that these constructions have to three manifolds. So we saw earlier by the result of, or by Theorem 2.4, every three manifold is cobordant to S3. Every three manifold bounds a four manifold. So now we can ask more specific questions. Well, what kinds of four manifolds can a given three manifold bound? Oops. You know, can a given three manifold bound a definite four manifold? And there's a primary example for when that happens. Lin spaces bound these canonical definite four manifolds. So remember that the Lin space LPQ, and we're just picking P to be bigger than Q to be bigger than 0. This is homeomorphic to minus P over Q surgery on the unknot. And if I can find a continued fraction expansion of the fraction P over Q, then I can realize LPQ as surgery on this link. So if I have an algorithm, right, if I can find a way to make sure that my continued fraction expansion of P over Q gives me a negative definite four manifold, then I'm in the clear. Unfortunately, sorry, there is a unique way to do this. With each xi at least 2 an integer. And I'm running short on time here. I'll do one quick example. So let's look at the fraction. So let's try and understand L54. I'm going to do something that might look that's going to look a little strange here. So, and this is ultimately, this is like the reverse of the Euclidean division algorithm. So I need to multiply 4 by 2 to get to get a number bigger than 5. Oops. I get 8. 8 minus 5 equals 3. And now I do the process over again. I need to multiply 3 by 2 to get something more than 4. I get 6. Minus 4 is equal to 2. I get 2. Need to multiply by 2 to get something bigger than 3. Subtract 2. No, I subtract 3 here. Sorry. I subtract the previous term in my list going down this way. I get 1. I need to multiply by 2 in order to get 2 minus 2. I get 0. My process terminates. So I guess I'll leave as an exercise verify that L54 is homeomorphic to this, this manifold presented by surgery. And also prove that this 4 manifold is negative definite. Yeah, I wanted to describe a way, sort of like a canonical way you can find a negative definite 4 manifold whose boundary is a given Lin space. Because I also wanted to ask the question, can we determine, right, like can we ask if a given Lin space bounds a rational homology 4-ball? So that is to say, right, it's a 4 manifold. The boundary of the 4 manifold is the Lin space, and the homology of W with rational coefficients is the same as the rational homology of a B4. And so the construction that I wanted to get at is that if I have this rational homology 4-ball W, and its boundary is LPQ, well, I know that I also have this, what I was describing earlier, I know that I also have this canonical negative definite 4 manifold. So if I just reverse the orientation on W, I'll reverse the orientation on the boundary, and then I can glue these two, right? I can glue these two boundary components together. And so this big manifold I'll call Z. And what can we say about Z? Z is closed. It'll be an exercise in the problem session to say that Z is negative definite. Oops, negative definite. And so then by Donaldson's theorem, the intersection form of Z is diagonal. Right, Donaldson's theorem says that if I have a closed definite manifold, closed definite smooth manifold, then its intersection form is diagonal. And so in 2007, Liska used this approach to actually use this lattice theoretic approach to actually classify which Lin space is bound to rational homology four-ball. So this is actually answered. And there are some problems in the problem set that I designed for today that are aimed to get at this construction, and what you can actually glean from this construction, and how you can get an obstruction to a Lin space bounding a rational homology four-ball. But now I really am pushing it, so I'll call it a lecture there.